In this example, let's consider that we're given the moment in the beam, so we know m of x, and we'd like to determine what the stress, so the bending stress is in the beam. So we'd like to determine what sigma is equal to as a function of x and y. So y being the vertical coordinate on the cross section, x being the longitudinal coordinate in the beam. So now, first thing is that if I know what the moment is, that means I know what the curvature is. And the curvature then is just simply the moment divided by EI for the beam. And the way that I'm going to get to the stresses is I'll go from the moment to the curvature, curvature to the bending strains, and the bending strains to the stresses. So firstly, we use the relationship we derived in the last example, which is m is equal to EI kappa, allows us to determine kappa in terms of the moment, so m over EI. I can now compute the strains, the bending strains, they're minus y kappa, so in this case it's minus y m over EI. And now I can multiply by the modulus, and I can actually get the bending stresses. So multiplying by the modulus, so sigma is equal to E epsilon. If I multiply it through by E, I end up with minus my over I. So I get this linear variation of the stresses on the cross-section as a function of y, and the variation in the x direction is handled through m as a function of x. If we go ahead and make a plot of this, we can also get an idea of how the system's behaving mechanically. So suppose I consider the beam and I have a positive bending moment, m of x. That means the beam is going to bend into some kind of smiley shape here. And if you think about what's happening to the material at the top, I have compression here and I have tension down here in the bottom. So the bottom fibers of the beam are being pulled in elongation, so I'm going to end up with tensile stresses, and the top fibers of the beam are being compressed together, so I'm going to end up with compressive stresses. And if we go ahead and look at this relationship here and plot it on the cross-section of the beam, sigma xx here, the bending stress, versus y in the beam, we see that we have negative values in the top and we have positive values in the bottom. So we end up with tension in the bottom and we end up with compression in the top of the beam. So that's important to sort of observe about the bending behavior of beams.